Okay. So hi everyone. My name is Shijia, and I'm assistant professor at the University of California, Merced. So I have been working on device-free human sensing for about 8 years, and I'm happy to share some thoughts and our progress on this topic here. So the work I want to introduce today, I'd like to summarize as Sense for Less, where we utilize physical knowledge to adapt the cyber-physical sensing systems and reduce the resources required for human sensing. So with the rapid development of the computing, we see nowadays various cyber-physical sensing systems has been designed to capture human information, and hence we are able to enable a lot of different smart building applications. However, the human information, this concept is quite broad, and the scope for this talk, I would love to focus on the context or action level human information. And what does it mean is that we want to know the identity, location, activity, physical condition, this type of information for the indoor occupants. So as we know, there are various sensing modalities are explored to achieve the human information acquisition. And we often categorize them into device-based and device-free systems. For device-based system, they would rely on the user to carry a device with specific sensor on it. It could be your mobile phone. It could be various wearables that you see in the market nowadays. And it could also be the emerging technology that where we call earables, which focus on the on-ear sensing for physiology level information gathering. And on the other hand, for the device-free system, they often rely on fixed infrastructure sensors in the environment. That is, a human does not need to carry the device, hence a device-free, such as vision, passive RF-based methods, light-based sensing, all these different modalities. So they rely on their measurable phenomenon that is induced by the human environment interaction to enable the information inference. So we focus on the device-free human sensing for a few specific applications, such as patient or elderly long-term in-home monitoring. So this is because not all the target are able to or will remember to wear or carrying their smart devices all the time. Furthermore, especially for long-term continuous monitoring, the device-free method would have its unique advantages. Despite the fact it sounds really great for the target application, we still face a lot of challenges. So I always like to start with an ideal scenario, ideal setting for systems. So what if we have unlimited resources? If we have unlimited sensors, storage, computing power, labels, data, then detecting the human information while the device-free and in device-free human sensing will actually be easy. But this, I hope you guys agree that this is ridiculous in the figure. So how can we acquire more human information through sensing, but with less resources? That's a question we want to answer. So the first challenge I would love to discuss here is how can we use less sensor, but acquire more information? By less sensor, I mean for the in-home long-term person monitoring, it's important to reduce the number of sensors needed for multiple reasons. To reduce perceived privacy intrusion, to reduce the cost, and to reduce the system's impact on the target. By the impact on system's impact on the target, I mean the less sensor or less impact from the sensor is actually important for the like real world deployment, so that the deployment itself would not influence the monitoring target. Imagine you put a sensor everywhere in a nursing home, and the elderly have to avoid them while they walk, then that would be bad. And by more information, I mean for many emerging applications such as mental behavior profiling or fall risk prediction, fine-grained and continuous information are required to acquire the high-resolution information so that we can enable accurate inference. So how can we achieve these? Our answer to this question is to use structures as sensors. The intuition is that people are causing physical vibrations all the time whenever you are interacting with the environment, which means we can acquire the fine-grained action level information by monitoring this vibration caused by people. Furthermore, because the vibration travels far in the solid, which would allow us to use less sensors to cover a room area. And since we are indirectly infer the human information, it provides non-intrusive monitoring and provides a better perceived privacy. So for a feasibility check, so we place a sensor in the hallway where we ask a pedestrian to walk by. So we can observe that the footfall on the floor actually causes the floor to vibrate, and the sensor we put in the hallway, it's a geophone here, can capture this vibration induced by the footfall, and you can see the detected signal are marked in the red box on the top figure. So with this intuition, we summarize the structure as sensor framework as follows. So people interact with their ambient environment, the object, the structure in the environment all the time. So this interaction would cause the structure, such as floor, the wall, the bed, it'll cause this structure to vibrate. And our system would acquire this vibration data, conduct the signal characterization, and eventually be able to learn or modeling the information. And that's how we acquire the human information. So the part where we utilize the understanding of the structure, for example, the property of the relay lamp waves, to extend the system's sensing ability so that it will allow accurate information inference, is what we call structure as sensors. So let's look at a simple example of type of information we can get through the structure as sensors. So here we look at how can we acquire the pedestrian identification information while they walk by. So the intuition is that different people, they walk very differently. They have their own walking pattern. For example, the top figure here, person A, when he walks, he kept his center of gravity more linked to the center, and his first striking angle is quite small. On the person B on the bottom figure, she walks while her center of gravity leans back and with a like larger angle when her foot strikes the floor. So we always joke with these two persons that the person B, who walks with more relaxed gait, is actually a master's student, while person A is a PhD student. Sometimes we say the person B walks with more relaxed posture because she knows when she will graduate. So because of this difference in their walking pattern, their footstep-induced vibration shows very different time and frequency characteristics. So we can see in the center figure, that the time domain signal shows very different slope and the peak. And because of that, their frequency domain signal shows different peak height, different peak location in the frequency. So these are the features that we can use to distinguish different people based on their footfall-induced vibration. And we did that, and we did some real-world experiment where we try to identify 10 people, where we get 99% identification accuracy. So the takeaway message here is that we can extend the sensor's ability to sense human information non-intrusively while using structure as a sensor. And here are some examples how our system working in action, where we put the set up the system in the nursing home for the gait monitoring, set up in the sleep lab for the sleep stage monitoring, and we even put up in the pig farm to detect the pig activity. So in summary, we are able to sense with less sensors by understanding the structure property, understanding the physical knowledge about the structure, and turn the structure into part of the sensor. The problem solved? Actually, not really. Let's take a look at what's behind the scene of all these wonderful systems. So all these great abilities to sense actually rely on the hardworking graduate student who spent a large amount of time to configure the system in the first place. So the second challenge we're targeting is how can we set up the system, or how can we make our system require less configuration efforts. With less configuration efforts, we'll be able to achieve large-scale residential deployment easier, especially for those require the calibration for different environment, and especially for the systems that rely on multiple sensors collaboratively computing. So our answer to that is the let's first look at an example where we want to configure the absolute sensor location. So many IoT systems would need to know the anchor or the device's absolute location to achieve tasks like localization, and the system would need the spatial information of the device to conduct, for example, human activity recognition. So, but now many of these systems are manually configured by the installer or experts, and this would limit the scalability or pervasiveness of the system. So our answer to challenge number 2 is to utilize the cross-modality context modeling to achieve IoT system auto-configuration. So the intuition is that for those developing sensing modalities, such as vibration-based human sensing, they may be co-located, even just temporarily, with other modalities. For example, vision is a very well-developed sensing modality, which can acquire the various information relatively more accurate and easier. So why don't we use this more developed modality to help with the developing ones with their configuration? So to do so, we would rely on their shared sensing context. And in the case of the structure vibration sensing, the structure as sensors, it is the occupant's first step location in the sensing area that we can use, that can be captured by both camera and the structure vibration sensor during their sensing task to achieve this auto configuration. So when a person walks by a sensor, their first step induced a signal, which is circled in the red box. You can see it'll increase when the person approach, and a decrease when a person leaves. So this increase and decrease pattern can be profiled to localize the footstep, the relative location of the footstep to the vibration sensor on a one-dimensional path. And on the other hand, the camera can recognize a person's posture easily nowadays in the camera view and assign the absolute footstep location to the anchor point for each footstep. So if we associate the peak of this footstep location detected by the vibration to the absolute footstep location measured by the vision, we can actually directly estimate the absolute vibration sensor's location through this data-driven approach. However, this pure data-driven approach would work well on an ideal floor with a simple wave propagation model. But in real life, the structure elements, such as beams and partitions, they would directly impact the signal characteristics. For example, in this case, the signal energy profile for the ideal floor will no longer be valid. Instead, we'll observe a different profile like this. And if we still rely on the pure data-driven approach we mentioned earlier, we would end up with a wrong sensor location estimation. So what can we do? So it turns out this type of beam effect has been well studied in the structural and the mechanical engineering. So figure here shows a simple model for the floor slab, of a floor slab of length L, where we see a force is applied to the point on the floor that is xf distance away from the beam on the left-hand side, and the displacement of the point on the floor that is xs distance away from the left beam can be calculated with the equation listed down here. So I'm not going to go into the details of the equation, but what does it mean is that with knowing beam location, we can actually estimate the footstep signal energy profile for a given sensor location, the XS. So with this insight, we adapt our data-driven model to achieve accurate sensor location estimation. So for the physical model side, we do a grid search on vibration sensor location. For example, here, XS1, XS2, and XS3. We would estimate the footstep signal energy profile based on the location, footstep location captured by the camera and the equation in the previous slides. And for the data-driven models, we extract the footstep-induced vibration signal to model the footstep signal energy profile as shown as an observation here. Then we will find the physical model that has the most similar profile comparing to the data-driven model, the observation, and consider the corresponding vibration sensor location, in this case, XS3, as the estimated sensor location. So we evaluate this scheme in the real-world scenario and compare our method that considers the beam effect, consider the physics model to the pure data-driven approach as a baseline. So we can see that for the baseline, without the physics model's adaptation, it shows an approximately 2 meters estimation error, while our approach achieved up to 7 centimeter estimation error on average. So the takeaway message here is that we can repurposing the sensing data for human-free device configuration while multimodal physical context modeling. So we did some related work in terms of how to auto-configure the cyber-physical systems, including how can we achieve auto-pairing between wearable devices, how to auto-configure infrastructure sensing device-free systems, and how can we do that systematically by understanding the quality of their deployment, their sensing quality. So now let's say we can easily deploy a system and make the building smarter. Is a problem solved? So as we mentioned before, for these device-free systems, they are relying on the interaction between human and the physical world to infer the information. And the physical world is always complicated and impacted by many different factors and effects. So if we only rely on the pure data-driven approach, we're gonna need a very large amount of label or data to cover all the scenarios. So our third challenge that I'd love to discuss here is how can we learn with, how can these cyber-physical systems, how can these device-free sensing systems can learn accurately with less data or less labeled data, because the data distribution change would happen over different sensing conditions. And just like any physical system, the labeled data is very difficult to get. So let's get back to the, revisit the pedestrian identification problem. So let's see how much data we need to identify a person. So we further look at the 10 people's data, where we plot the number of trace. Trace means a continuous walk with multiple footsteps being detected. We compare the number of trace used for training and the identification accuracy. So we can see at the 6th trace, it's the accuracy is quite high already. It's 98% accuracy for the trace level identification, where we combine multiple step level classification result within a consecutive walk of a person. So this is very inspiring. You only need to walk 6 times to be able to identify it. So we got a little bit cocky, and we did something we refer to as cookie test, where we put a jar of cookie at the end of a hallway and tell the testing, like the human subject, which are all the students, that they are free food. So we got our cookie test trace level detection rate back, and it's about 72% accuracy, even for the trace level identification. So what went wrong? Turns out people's gait, which is what we are relying on to identify the people in the first place, their gait changes when they walk at different walking speed, or here we refer to as a step frequency. So you can see for the top 2 figure, where when people walk at a high footstep frequency, their ankle of the foot strike is larger, their step length is longer, and all this difference would induce the difference in the footstep induced flow vibration, as showing on the right-hand side. You can see for the top figure, that's collected when people walk at a higher footstep frequency. The peak location, the duration of the signal are quite different from the bottom figure, where the same person walks at a lower footstep frequency. So imagine if we train the model, the pure data-driven model with the top signal and the test on the bottom signal. Of course, we cannot like re-identify the person. Even for the human eyes, I wouldn't consider those 2 signals are similar. So still, we always start with simple solutions. A very simple solution is, let's just gather data from all walking speed, all the different footstep frequency. If you get that, you'll get back to the 98% accuracy. But this simple solution It's as simple as asking your grandpa to walk in hallway 1,000 times, probably different speed, different shoes, wearing different, or using different walkers. That will be too much. So our answer to this is we need to further understand the data distribution change. So we ask the person 1 to walk at 7 different walking step frequency, different speeds. For each step frequency, we collect 35 steps from the same person. And we put all this over 200 footstep signal together and cluster them based on their similarity of their waveforms. And turns out we discovered there are 3 different clusters among all these over 200 footsteps signals. And what's more interesting is that these clusters, they are distributing over different step frequencies. For what that is mean is that the cluster 1, the waveform showing as a cluster 1, occurs more often when the person walks with a high footstep frequency, while the cluster 2 occur more often when people walk at a medium or low step frequency, while the cluster 3 mostly just occur when people walk really slow. So we further look back, what happened to our cookie test? So it turns out when we do the training, we collect the data where people walk at a more of a medium step frequency. And when the students get very excited about the cookie, the free cookie, it turns out they walk slightly faster. It's cookie, who wouldn't love it, right? So what does it mean is that our training set and the testing set are actually consist of mostly cluster 2 and the cluster 1 signal separately. So that is the reason our pure data-driven model failed. So we did make another observation here is this data distribution change, this cluster appearing percentage, actually it changes very smoothly with the step frequency. Instead of, say, cluster 1 occur in the 2nd level or 5th level, they change very smoothly. So this gives us an inspiration. Can we utilize prior work on the transductive transfer learning? So prior work on this gives us the intuition that the transductive transfer learning can take unlabeled data into account when modeling. But they do have the assumption or limitation where the unlabeled data and the labeled data needs to have some similarity in their distribution. So in the left figure showing here, the labeled data are marked with a triangle and the unlabeled data are marked as a circle. This is a toy figure for the binary classifier. So we can tell that if the distribution of the unlabeled data is close, similar to the labeled data, which we marked with a darker red here, the system can still be able to model the classifier. But for the data distribution that has a significant difference, it won't be able to classify them accurately. So this is an observation, and let's revisit the other observation we made slightly earlier, where the data distribution changed smoothly with the physical attributes, in this case, a footstep frequency. So can we do something here? In fact, with this knowledge, it will actually allows us to know which part of the unlabeled data, given the labeled data, can be accurately predicted. So for example, here, If the y-axis is first step frequency, we will know for the dark colored unlabeled data point, which is closer or very similar to the labeled data in terms of the first step frequency, we'll be able to predict them accurately. So with this idea, we propose an iterative learning guided by physical attributes. We propose a new learning framework where we first understand the relation between the directly measurable physical attributes, and in this case, the first step frequency, and the data distribution changes. So once we understand this relation, we'll be able to handle the similar data distribution in each iteration. And at the end of each iteration, we will be able to expand the model by labeling the unlabeled data for those with high prediction confidence. As shown here, we are labeling those that we predict with high confidence. And then in the next iteration, with this newly labeled data, the system will be able to handle more data distribution changes. So the model can cover the physical attributes with a larger range, and so on and so forth. After iterations, the model will be able to cover all the data distribution that's been collected. So the key here is that we're utilizing the physical attributes to control the iterative learning order. So that's a key part that enables this iterative learning. So we did the real-world experiment again with 10 people, and we compare our iterative learning method IT-SVM to the supervised learning SVM support vector machine as baseline, and we only provide the label for the medium step frequency, and we can see for the support vector machine, it works quite well if the training and testing data are from the same data distribution. But once the data distribution change are significant, say the step frequency low and extreme low and high step frequency, the accuracy drops significantly. And for the low step frequency, it even dropped to 10% accuracy. And since we're identifying 10 people, that's almost a random guess. But if we are using the iterative learning model that expand the model through multiple iterations slowly, we'll be able to achieve up to 3 times improvement in those extreme cases. So the takeaway message here is that we developed this transfer learning framework that's guided by the physical attributes to handle the target condition variation. So other than the iterative physical attributes guided iterative learning, we further explore other learning algorithms. For example, the physics guided transfer learning to handle the structural variation, the semi-supervised cross-granularity learning to handle the different different granularity of the labels. And that's what we did to try to use less data or less label data to still acquire more information or high accuracy of information in the device-free human sensing. So in conclusion, we did both in the system perspective and the data perspective to try to make the system sense better with less resources. We use vibration as a common modality to reduce the number of sensors needed. And we used multimodal IoT system and their complementary information to automatically configure the system and reduce the configuration efforts. And from the data perspective, we studied the data distribution change and its physical meaning to improve the classification accuracy with limited initial labeled data. And that's the end of the talk. Please let me know if you have any questions.